So we left off talking about the binomial distribution and how we can use it to model the performance of a baseball player getting 3 at-bats in a game, such as Ben Zobrist in the upcoming Game 2 of the 2015 World Series for the Kansas City Royals. So Zobrist's batting average is .333, which we interpret to mean that he has a 33.3% chance of getting a hit any given time that he goes up to bat. If he has 3 at-bats in the next game, we'd like to know what his probability distribution is for how many hits he's going to get in those 3 at-bats. Now we figure this out by taking the probabilities respectively of success and failure, .333, and 1 minus .333, which is .667, and then determining what outcomes correspond to those different eventualities. So for example, if we use the letter H to represent a hit and O to represent an out, then going 0 for 3 means out, 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 that all 3 of his at-bats he did not get a hit. Going 3 for 3 means hit, hit, hit. There's only one possible way to do that. But going 1 for 3, there are several different ways to accomplish that. We could get a hit in our first at-bat, and then the other 2 are outs, or the 1 hit that we get could come in the second at-bat, or the 1 hit that we get could come in the third at-bat. So there's 3 different possibilities, 3 different outcomes in the sample space, which all correspond to the same value of 1 for the random variable recording his total number of hits. Likewise, going 2 for 3 can happen in 3 different ways, corresponding to the 3 different at-bats in his day where he could get out instead of getting a hit. So we used these because each of these events is equally probable in our sample space full of 8 outcomes in total, to say, well, there's one way to go 0 for 3, one way to go 3 for 3, but there's 3 ways to go 1 for 3, and 3 different ways to go 2 for 3, so we need to account for that when we compute these probabilities. Now, how likely is each one of these different ways to happen? Well, let's take 0 for 3, for example. That corresponds to him getting no hits at all, so failing 3 times in the language that we're going to use here, and succeeding none of those times. So what's the probability that he's going to fail all 3 of the times? Well, assuming that these events are independent, that whether or not he gets a hit on each at-bat doesn't change how likely he is to get one on his next at-bat. The probability of failing 3 times is the probability of failing once multiplied by itself 3 times. So Q times Q times Q. Fail, fail, fail. That's another name for Q to the power 3. And since Q, the probability of Zobrist not getting a hit is .667, this Q to the third power is about .297. And since there's only one way to make this outcome happen in our sample space, the probability of him going 0 for 3 is 1 times that .297. Likewise, for 3 for 3, the story is relatively straightforward. This corresponds to 3 successes and no failures. And since the probability of each success is P, and the events are independent from one another, that means that his probability of getting 3 successes is P times P times P, which is another name for P to the power 3. So multiply his batting average, .333, by itself 3 times to get the probability .037. And since there's only one way to make that outcome happen, his probability of going 3 for 3 is 1 times .037. And so the story only gets more interesting when we start to shuffle up the number of successes and failures. For example, how likely is it that he goes 1 for 3, corresponding to 1 success in his 3 at-bats and 2 failures? Well, the probability of him getting 1 success, 1 hit, is .333, his batting average, P. The probability of his getting 2 failures, if they're independent, is Q, his failure probability, multiplied by itself once. So P times Q is the probability of him getting hit out, out. But that's not the only way that he can go 1 for 3. There are 3 other possibilities. So when we get the probability of P times Q, in other words, P to the first times Q to the second, it's not the same as the probability of him going 1 for 3 until we compensate for the fact that there are 3 different ways in which he can do it. So P to the 1 times Q to the 2, which comes out to be .148, multiplied by the number of ways that it can happen, which is 3, gives us the probability of him going 1 for 3. In this example, it's .444. Similar story for going 2 for 3. Going 2 for 3 means having 2 successes and 1 failure, the probability of the 2 successes being P times P, the 1 failure Q to the power 1. Multiply those together, you get .074 for Zobrist, but there are 3 different ways for him to do that, and so the probability of going 2 for 3 is 3 times .074, or .222. So this is a complete probability distribution, theoretical probability distribution, for how many hits Zobrist will get in his next game, if his odds of getting a hit every time he steps up to bat are .333, and he's going to go up to bat 3 consecutive times, with his performance being independent on each one from his performance on the last. So that's a complete story for a 3 at-bat game, but we did a lot of work to get to that. What we'd like to do is get to a formula that will let us determine these probabilities without having to explicitly list out all the possible outcomes, for example. Because while it was relatively simple to do in a 3 at-bat game, just imagine what we would have to do if it were a 6 at-bat game. So I took the time to list out all these possible different outcomes. It took me forever. But you can imagine if we were to do this, we could count them all up and figure out that the number of ways that Zobrist could go 0 for 6, there's only one. He gets out every time. There's also only one way that he can go 6 for 6. He gets a hit every time. But as soon as we're in the middle, there's actually 6 different ways for him to go 1 for 6, corresponding to the 6 different at-bats where he'd get his 1 hit. And likewise, there are 6 different ways for him to go 5 for 6. And then it gets even more complicated. There are 15 different ways for him to go either 2 for 6 or 4 for 6. And there are 20 different ways for him to go 3 for 6. So if we wanted to get the probabilities out of this, we would have to multiply those numbers by the products of the success and failure probabilities that correspond to those outcomes. So for example, going 6 for 6, we would multiply 1 by p to the 6. That corresponds to 6 successes, 6 hits, each having a probability of p, and they're all independent from one another. And in order to go, for example, 2 for 6, not only does he have to get those 2 hits, but he also has to get out 4 other times. And so we also need the probability of failing 4 times as part of that probability distribution there as well. So this would, again, give us all of the probabilities that we would need if we plugged in the values for P and Q that we have for Zobrist. The problem is I don't want to have to list out all these outcomes in order to determine this column right here, the number of ways in which he can make these different outcomes happen. So what we'd like is a formula that can do that for us instead. And what we're going to find a formula for is a distribution for what's called a binomial random variable. By definition, a binomial random variable is the sum of n, capital N, independent and identically distributed Bernoulli random variables, each whose success probability is equal to p. A shorter way to say that is a binomial random variable records the total number of successes in a series of n independent trials, each of whose success probability is equal to p. So examples are Zobrist getting 6 at-bats in a game, flipping a fair coin 20 consecutive times, making a classroom of 25 randomly selected students. That's going to take Math 110, right? That n is the number of trials in each case. In the at-bats example, it was 6 at-bats. Each at-bat is a trial. In the coin flipping, it's 20 flips. In the example of making a classroom full of 25 randomly selected students, each trial is we pull a student at random out of the student population. So that's our capital N. It's how many trials we're doing. And then each of those trials has a success probability associated with it. In the case of Zobrist's at-bats, that probability is 0.333, the probability of him getting a hit when he goes up to bat once. If I'm flipping a fair coin, the success probability is the probability of getting a head on a fair flip, which is 50%. If I'm looking for the probability of getting certain numbers of female students out of a student population which is 61% female, as Bridgewater's is, then the success probability here would be 0.61. So identifying what is n and what is p is probably the most important thing to do when you encounter something that looks like it could be a binomial random variable, because we're going to use those parameters in the formula that we're about to meet. And here's the formula. If x is a binomial random variable, it records the total number of successes in n independent trials, each of whose success probability is p. So we'll say it's an NP binomial random variable. Then the probability of getting x successes in that series of n trials is given by the formula that you see right here. So this formula looks really nasty. I have to explain kind of what's going on here. The first thing you see is this weird expression called NCX, sometimes called N choose X. That's standing in for the number of different ways that we can arrange X successes among N trials. So we'll call that the ways. After that comes P to the power X. That's going to be the probability of succeeding X times. Right? So it's the probability of succeeding once multiplied by itself with a total of X factors. That's why it's P to the power X. And finally, we have the probability of failing the other N minus X times. The probability of each failure is 1 minus p, which we also know as q. So that's really what's going on here. This is just a formulaic way of packaging together the calculations we did a couple of slides ago. And so this tells us what's the probability of having x successes in n trials. Now all we have to do is figure out, again, how to come to grips with this part of the formula. How do we figure out how many ways there are to arrange x successes among n trials? What we get is something called a binomial coefficient. It's read as n choose x. And the quick way to compute it, So there's a formula for it down here at the bottom, but the way that I like is start by making a fraction with n on top and x on the bottom. So the numerator is n and the denominator is x, whatever those are for your given situation. Then start decreasing the denominator by 1 and multiplying by it. So if I start with x, I'm going to then multiply by 1 fewer than x. And every time I do that in the denominator, I'm also going to do it in the numerator. So I'll multiply n by 1 less than n. And I'm going to continue decreasing the denominator 1 more and multiplying by it again and again and again, until eventually I run out of numbers in the denominator, and at that point I stop. So I end up with exactly as many factors multiplied together downstairs as I had upstairs. That's the quick and dirty way to compute a binomial coefficient. So let's see it in action by asking the question for Ben Zobrist, what is the chances that he's going to go 4 for 6 in his next game if his batting average was .333? So the number of hits that he gets in 6 at-bats we're going to model as a binomial random variable, where n, the number of trials, is his number of at-bats. That's 6. P, the success probability, is the probability of him succeeding in any one of those at-bats. That's .333. Q is the probability of him not succeeding on any given one of those at-bats. That's 1 minus P, or .667, the probability of him getting out. And then X represents the number of successes that we desire. And if the question's asking what's the probability of him going 4 for 6, then the number of successes here is equal to 4. So, how do we compute this probability? There are 3 things we have to multiply together. The number of ways of arranging 4 hits among 6 at-bats, the probabilistic contribution from 4 successes, and the probabilistic contribution from 2 failures. So those are the 3 different things we're going to have to multiply. First of all, the contributions from successes and failures are relatively straightforward. The success contribution is just p to the power 4, and since p is .333, that's .333 raised to the 4th. Likewise for the failures, that's q to the power 2, .667 to the power 2. By the way, a quick check on yourself is that these 2 exponents should always add together to give you the total number of trials that you're doing. Right? So in order to succeed 4 times in this example, he has to fail twice. In order to get 4 hits, he has to have 2 at-bats where he doesn't get hits. Okay, so now let's tackle that nasty binomial coefficient, which we're going to read over here as, quote, 6 choose 4. It's the number of ways of arranging 4 things among 6 spaces, those 4 things being his hits. So how do we do it? I'm going to set up a big fraction, and I'm going to start the fraction with a 6 on top and a 4 on the bottom. And then I'm going to proceed by multiplying the denominator by 1 fewer, so 4 multiplied by 3. When I do that, I'm also going to multiply the numerator by 1 fewer than it. So 4 times 3 on the bottom, 6 times 5 on the top. And then I'm going to keep going. Downstairs decrease again to 2, and upstairs decrease again to 4. Again, downstairs decrease to 1, upstairs decrease to 3. And at this point, I have to stop. Right? If I went one further step, I would multiply by 0, and the whole world would implode up on itself. So we're going to stop right there. We end up with as many factors upstairs as we have downstairs. That means we're ready to simplify this computation. 4 times 3 times 2 times 1 is 24. 6 times 5 times 4 times 3 is 360. And when we divide those two, we get 15. One of the surprising things is that this is always a whole number. Even though it looks like it could be a fraction, something that's not a whole number, it always ends up being a whole number, which is mathematically very important. So in other words, there are 15 different ways to arrange Zobrist's 4 hits among his 6 at-bats. And each one of those different ways is going to have a probability to happen of .333 to the 4th times .667 squared. So his overall probability of going 4 for 6 is going to be the product, 15 times .333 to the 4th times .667 to the power 2. Finishing that computation, doing the exponents first and then doing the multiplication second according to the order of operations. Using a calculator, I get .082, or 8.2%. So to compute a probability for a binomial random variable, the steps are really that simple. We have to know, first of all, what are the values for these parameters? The n's, the p's, the q's, and the x's. How many trials do we have in this problem? What's the probability of success on each trial and therefore failure on each trial? And how many successes are we asking about? Then, we just have to multiply these 3 different factors together. The binomial coefficient being the one that's going to take the most work, but which we can find just by setting up a fraction whose numerator and denominator are n and x respectively, and which then decrease in both numerator and denominator by 1 until we run out of room in the denominator. Then we'll stop and compute. Multiply that number by the success probability raised to the power of the number of successes that we want. Multiplied also by the failure probability raised to the power that's equal to the number of failures that we want. At the end of that whole process, we get the probability we're looking for.